Hello, everyone. So with this video, I'm hoping to cover only a subsection of the course notes that were posted for you on Brightspace, and basically only those items that will help you size and come up with the structural elements that you're looking for Project Brief 2. We'll cover some of the other elements as they pertain to future briefs, but at this time, I wanted to get you going with your Project Brief 2. So what you have on your screen is what we're going to be starting with, which is the estimation of the size of a control joint. So in this case here, I just want to show you what we have. I'm pointing out to you first what we're looking at. So we have a control joint here, which is something that is sawed. It's an opening, it's a cut that's actually sawed into the concrete to ensure that you force the cracks to happen at very specific locations where you want them to happen in a slab. Okay. I'm also illustrating here the presence of a poly barrier that's separating the underside of the slab from the soil beneath it. So we're going to basically estimate that the dimension of that element. We're going to assume that we're going to have some rebar of some sort. It's not important what kind of rebar we have here. That's beyond the scope of this example. And then we're going to size what the cover of concrete is going to be. So by cover, what I mean is exactly what this says, which is how much concrete is covering the steel that is closest to the surface. So in this case, according to this table in your textbook, table 22.1, page 553, you're going to be using 2 inches of concrete cover. That's exactly what this is. So as you can see, that's the distance from the outermost surface of the concrete and the closest rebar. We also have rebar that's going into the page right here. Okay. And lastly, to size the control joint, we simply figure out what the depth is of that slab, and we'll see in a few moments different ways of figuring out the depth of that slab. But if you have the depth of a slab right here, in this case 6 inches, the rule of thumb, according to section 22.11 on page 558 of your textbook, is you take the thickness and you multiply it by 0.25. So in this case, you get 0.25 times 6 inches, you get 1.5 inches. You round that up to the nearest set of inches, that gives you 2 inches. So you'd make sure that the depth of that control joint you're going to cut into the slab is 2 inches. What is the width of that control joint? So this horizontal dimension, the width of the cut in there, it's plus or minus 1/8 of an inch. Okay. Lovely. So let's move on then to locating the control joint on a slab. We have a slab located as such. It measures 65 feet by 65 feet. And I'm just indicating where the slab edges are and the various control joints. The control joints are being shown in those thin crosshatch lines. Okay. Now, in a 65 feet by 65 feet slab, where do we put the control joints? Well, the first thing we have to figure out is what the thickness of the slab. In this case, we have 8 inches from the previous slide, but you'll notice on future examples that we'll be doing a few slides in, different ways of calculating the concrete slab. We also found from our previous example that the control joint will be 2 inches deep by 1/2 and 1/8 thick or wide. So what do? We're going to look at this rule of thumb right here, and that is the spacing of control joints is determined by multiplying the thickness of the slab, T, by 24. So in this case, the thickness of the slab is 8. Multiply that by 24, you get 192 inches or 16 feet. The maximum spacing you are allowed for these control joints is 15 feet. So you come up with an equal number of spacing, then you get a nice round number that is less than 15 feet. You're allowed to go up to 16, but 15 is the max in this case. So in this case, I played around with it, and the closest round number in feet that I came up with was 5 equal spacing of 13 inches on center. And that's kind of what I'm trying to show right here. Okay? Rules of thumb. And make sure you check out some of these other items that I'm showing here, because that's where you find this information. All right, moving on. Clean up a little bit. Okay, so let's try to estimate the size of the slab for a set of, I don't know, construction drawings. Okay, so what we have here, what I'm trying to show here, is a series of grid lines, 1, 2, 3, 4, 5, going east-west. Okay, I'm just showing 1 and 2, but it continues 3, 4, 5, and so on. And I'm a series of grid line going north-south, A, B, C, and so on. I'm showing the first 2, but it continues. And these grid lines are at 20 feet, say. And this rule only works up to 20 feet max. So that means that the columns, because the columns are located at the intersections of the grid lines, the columns are located at 20 feet, no more. If you have columns spaced further apart than 20 feet, this rule of thumb will not work. Okay? Now, this rule of thumb also assumes that you don't have any drop panels. And you can refer to my video on assignment 2 as to what drop panels look like. Very well. So then, now that we have this, the rule of thumb to find out the thickness of the slab in a set of grid lines that has columns spaced no more than 20 feet apart is as such. You take the thickness of the slab is equal to the span divided by 30. Okay, so let's say in this case, if this, sorry, pardon me, I made a mistake here. This should have been 17 feet here. Sorry about that. You take 17 and you divide it by 30, which gives us 0.67 feet. I convert that to inches, it gives me 6.8, and to the nearest inch, that's 7 inches. So the thickness of the slab would be 7 inches. Okay. Okay. Next. I want to point out that this exactly is the same method you're going to use if you use metric units instead of imperial units. So you divide the largest span by 30, assuming that it's no more than 9.14 or so meters spacing, right? 20 feet. The one thing that I would recommend, though, is that if you're going to be using metric units, you basically round up your dimensions to the nearest 5 or 10 millimeters, depending on the preference of your working drawings for professor. Okay, so what we looked at was an example previously that works only up to grid line spaces of 20 feet. Okay, now if you have a grid line spacing that is more than 20 feet, the previous example is not going to work. The only way that you can work with more than 20 feet spacing is if you start including drop panels. And like I mentioned previously, drop panels, you can go and refer to them by viewing what I created as the video for assignment 2, our assignment 2. So let's say that you have more than 20 feet, okay? That the spacing is more than 20 feet in this case, right? So more than what we had in our previous example right here. Okay, so what do we do? Well, if it's more than 20 feet, then, or 20 feet or more, and this works only up to a maximum of 30 feet, we have to use a slightly different rule of thumb to figure out the thickness of the slab, and we must add these drop panels. So we'll talk about drop panels here, because here I'm going to show that's what this cut refers to. We'll look at that. But first, let's estimate the thickness of the slab. So the rule of thumb, if your grid lines are spaced at more than 20 feet, is this. You take the largest span and you divide it by 35, just like this. Okay, so in this case, let's say we have 20 feet. You divide by 35 and you get 0.57 feet. Convert it to inches. To the nearest inch, you get 7 inches. That is the thickness of your slab. So if I'm looking then at this cut through this slab and drop panel, that's this thickness right here. That's the thickness of the slab. Okay. Now I'm going to refer you also, as we start talking about drop panels, to drawing 23.17 in our textbook. Great. So let's move on. We figured out that the thickness of that slab is 7 inches. What about the rule of thumb for figuring out the thickness of the drop panel? Well, the rule of thumb is that you take the thickness of the slab and you multiply that by 0.25, just like this. Okay. So 0.25 times 7 inches is 2 inches. So that's going to be the thickness of the drop panel. That is this thickness here. Okay, how do we find the width of this drop panel, right? Because it's a square or a rectangle that's around the column. Well, the width is determined by finding this dimension. Okay, the rule of thumb that we have helps us find the half dimension right here. Okay, and you do that by taking the span, the largest span, and multiplying it by 1/6. So 20 feet times 1/6 gives us 3 feet 4 inches, okay, to the closest inch. That's simple. Next, we're going to look at how to identify one-way slabs. The reason this is important, identifying one-way slabs, is because it clarifies, it gives you directions as to how to figure out the thickness of the slab, how to figure out the dimensions of the beams supporting the slab, and furthermore, details about the reinforcing of that slab. So let's look at this. What I'm showing here is a series of grid lines, 1, 2, 3, 4, and so on. They're spaced at 32 feet on center, and then grid lines going north, south, A, B, C, and so on, spaced at 15 feet. Okay. So then I'm going to look at figuring out what the ratio is between the longest grid line dimension and the shortest grid line dimension. So 32 feet divided by 15 feet, right? 32 feet divided by 15 feet gives us 2.1. Okay. If that number, in this case 2.1, is more than 2, then this slab is considered a one-way slab. Okay, and this here is detailed even furthermore for you in our textbook, figure 23.2, page 570. So for this layout of grid lines, and this is how you do it, right? You find the largest grid lines going one way and the largest grid lines going the other way, right? As long as they match in the same panel, and you do the ratio of largest to smallest. So in this case, it would be the large dimension to the small dimension. And if that number is greater than 2 for that panel, or say this panel, then that's considered a one-way slab. Bigger than 2 is a one-way slab. Why is this important? Because if we know that it's a one-way slab, we're going to use this set of rules to figure out the dimensions of the slab thickness and the dimensions of the beam supporting that. So again, if you look at this isometric drawing that tries to show sort of like a 3D view of this, we're going to look at trying to figure out the thickness of this slab, so this slab here, as well as the dimensions of this beam supporting that slab, which is this beam here, right? This beam here supporting that slab on both sides, okay? All right, so let's identify first that the distance of 20 feet in this direction is from beam to beam. And then this distance, 24 feet in the other dimension, again, column to column, but it's the length of each beam from column to column, okay? So first things first, how to estimate the slab thickness. If we know that it's a one-way slab for this kind of setup, the slab thickness is equal to the span divided by 24, okay? The span divided by 24. And to be clear, the span that's meant here is the span between beams. So in our case, the span between this beam and this beam is 20 feet. So 20 feet divided by 24 is 0.83 feet, or to the closest inch, 10 inches. If you're doing this in metric units, whether meters or millimeters, I recommend millimeters. Maybe make it to the closest 5 millimeters or 10 millimeters, depending on the preference for your working drawings professor. Right, so we know the thickness of the slab, we get 10 inches, and that represents this dimension right here, okay? So now let's find the dimensions of the beam. The rule of thumb for the beams is this. The beam depth, so the vertical dimension, this dimension here for the beam, is equal to the span divided by 15. And the spanning case is the span of the beam. So that would be this dimension here, 24. 24 feet is the span of the beam. Do that number divided by 15, and that gives you the depth of the beam. So in this case, when you go through this process, to the nearest inch is 20 inches, or if you want to do it to the nearest 5 millimeters, you do it that way. So that's where 20 inches goes. 20 inches is this depth right here, okay? And then what about the beam width? The beam width is calculated as a rule of thumb by doing 0.6 times the depth of the beam. Again, 0.6 times the depth of the beam. In our case, the depth of the beam is 20 inches. So to find this, this width right here, you do 0.6 times 20 inches equals to 12 inches, which is right here. So now we have found that we have a slab that's 10 inches thick, a beam measuring 20 inches deep by 12 inches wide, so that this whole entire depth is 30 inches, right? 20 plus 10. Great. Moving on now to two-way slabs. So we found out that to find out whether or not it's a one-way slab, we get for any panel, the ratio of the longest grid line divided by the shortest grid line in that panel. So let's say if I rearrange the panel, the grid line dimensions, so maybe if that doesn't happen. So what we have here, grid lines going east to west at 22 feet. I'm just showing 3 of them. And grid lines going north to south at 20 feet. So let's do the same process. To determine whether or not it's a one-way slab or a two-way slab, we have to do the ratio of the long span to the short span. So in our case, the long span is 22 feet, right? 22 feet divided by 20 feet equals to 1.1. Because that number is less than 2, each one of these slabs are considered two-way slabs. That means they're bound on all 4 sides by beams. Now that has implications, as we'll see, and as we just saw for one-way slabs, about how to calculate the depth of the slab and the dimensions of all of these beams supporting the slabs on 4 sides, okay? So let's look at that. Let's find out how that's going to work. So I'm trying to show here sort of an isometric drawing, and the slabs are sitting on this beam, this beam, this beam here, and then there's a hidden, beam that I've cut off on this side. Okay, so I'm just showing the columns and the beams and not the slabs. And here's where the 22 feet span is. So in this case, we found, how do we find the slab thickness? Well, for a two-way slab, the slab thickness is found by taking the span and dividing it by 36. So in this case, the span of 22, right? You divide that by 36, and then I multiply it by 12 to get the answer in inches. So 22 divided by 36, you get an answer in feet. Multiply by 12 to get an answer of 7.3 inches. To the nearest inch, that is 8 inches. And that's exactly what we get here. That's 8 inches for the thickness of the slab. Now let's find the dimensions of the beam. The beams are calculated. First, you have to figure out what the depth of that beam is, and then we'll figure out the width. How do we find the depth of the beam? The depth of the beam, the rule of thumb is you take the span of the beam and divide it by 15. Okay, so in our case, the span of the beam is 22 feet. Okay, this dimension right here. So you divide by 15, you get 1.47 feet. Convert that to inches, to the nearest inch, that's 18. So that's what this depth is. 18 inches is right here. Okay, now what happens if your slab is such that the beams on all four sides of the slab, some of them have a different span? Go for the biggest one so that you come up with the biggest beam on all four sides. Okay, that's probably the best way to do it. Okay. Now let's find out the width of that beam. We know it's 18 inches deep. How wide is it? Well, the rule of thumb for beam width is right here. The beam width is the depth times 0.6, just like we saw previously. So if we take 18 inches divided by 0.6, that gives us 10.8 inches. Round it up to the nearest inch, it's 11 inches. So that's what this width is. So now we know that this beam is 11 inches wide. It is 18 inches deep, which means that this whole assembly now is 26 inches deep, right? 18 plus 8. Lovely. Coming close to an end. Now let's look at figuring out the dimensions of the columns, okay? And that's the cross-sectional area of a square column. Again, I'm showing here, for argument's sake, a set of grid lines that start at 1, 2, 3, and they're spaced at some kind of spacing. We'll find out in a moment what that is. And a set of grid lines going north, south, A, B, C, and so on. I'm just showing the first two, and we'll find out what that spacing is in a moment for argument's sake. The rule of thumb for figuring out the cross-sectional area of a column is this. You want to take the total floor area supported by that column, everything above it, okay? And then you want to divide that by 10 if it's lightweight concrete or regular concrete, or 20 if it's high-strength concrete. So that's not 10 minus 20. It's either 10 or 20. That works only for imperial units if you find the floor area in feet. Okay, so let's do this in feet, and then I'll show you in square meters or square millimeters. So the first thing you have to do is figure out the tributary area for an interior column. So that's this column here that I've illustrated for you, right? This one here. This is an interior column because you have grid lines that continue on one side, east to west, and on the other side, north to south. So the grid line is simply a multiplication, a product of the grid distances, east-west and north-south. Because I'm picking 32 feet north-south and 32 feet east-west, the tributary area for that column, interior column, is 32 by 32, so 1,024 square feet. Okay, but look at this. This building, or this column that we're designing, is for a 4-story building. That means this is a column on the ground level supporting 4 stories above it, right? So then what we have to do is multiply this area by 4, right? Because this column we're looking at is supporting 4 stories above it. So you multiply that by 4 and you get 4,096 square feet. Okay, great. What's next? Now we're going to employ this rule of thumb right here. If we assume that we have, regular concrete, lightweight concrete, we have to divide that floor area in square feet by 10, which is what we do right here. 4,096 square feet divided by 10. To the nearest square inch is 410 square inches. Okay. Now, if you choose to do the area in either square meters or square millimeters, either one, you then want to use not 10, but 1,404. So if you have the floor area in square meters and you divide by 1,404, you're going to get an answer for your column cross-sectional area in square meters. If you use a floor area in square millimeters and you divide by 1,404, you're going to get an answer for the cross-section of the column in square millimeters, okay? So for imperial units, it's 10 if you divide square feet and you get square inches. In metric, it's 1404. Okay, great. So now that we know the area of the column, 410 square inches, we take the square root, because it's a square column, to find what the dimension is for each side. So the square root of 410 is approximately 20.5 inches. Okay. Now you would repeat the same process then for high strength concrete, right? You would divide by 20 right here if you wanted to do the area in square feet, or you divide by 2,808 if you're going to use the area in either square meters or square millimeters. Okay. Now, the last thing that I'm not going to spend too much time on right now, because it will not directly affect your project brief 2, is reinforcing. Okay, reinforcing steel. We'll talk more about this later because it may affect some of your other project briefs, but I want to get this to you as soon as possible so you can rock project brief 2. All right. Now, this works fine for a square column. What do you do for a circular column? Well, for a circular column, assuming that you've been able to find what the dimension of the square column is, in this case is 20.5 inches by 20.5 inches, you can find what the area is, right? The area of that square is 420.25 square inches. Then that's the same area you have to match, but with a circular column. And how do you do that? Well, you remember that the area of a circle is equal to pi r squared. So then you simply rearrange that to calculate what radius is, because you know what the area is, right? It's 420.25 square inches, right? And pi is a constant, an irrational constant. So you simply put that all in under here. So you do this number divided by pi, and then you take the square root, and then you get a radius of 11.6 inches in this case. Or if you prefer diameter, you just multiply that by 2 to get the dimension of the diameter. That's how you come up with a circular column. Now, I have to say that if you're given dimensions for the columns in your project brief, you go for them. But at least this way you know how to come up with the dimensions for them, okay? All right, let's clean this up a little bit. And I guess then a few other things. Right, so I did some quick back of the envelope calculations to come up with some of the dimensions for possible elements in your project brief 2. Consider these upper values, okay? So the slab is up to 210 millimeters in thickness on all levels, okay? The garage slab, look at it from 820 to 850 millimeters. Your column dimensions for the square ones should be 600 up to 610, sorry, the biggest columns, which are the ones on the ground level, should be between 610 by 610 or 630 by 630. That's your range, okay? Unless you're given something different in your working drawings brief. Now, what this brings up to is this. That's the column on the bottom levels. If it's okay with your working drawing professor, then you can use that same column dimension everywhere. Otherwise, you should recalculate the dimensions for all levels, right? Because at all levels, the columns, as you go up, support less and less weight, right? They support fewer and fewer stories. So the area of the columns will get smaller and smaller. But if your professor wants you to use this dimension at all levels, go for it. For the circular columns, just come up with the equivalent area or whatever diameter you're given by your working drawings professor. For the draw panels, use up to these dimensions, okay? You can calculate it, but these should be some upper limits. And don't forget to go and check out assignment 2 for kind of what a drop panel looks like. And finally, drop panels at your shear walls should be used as 1100 width by 6.5 thickness. And that's 1100 from the wall, okay? And lastly, some upper levels then for the thickness of your shear walls. 200 millimeters thickness is good. the parapet at the roof, unless you're given different requirements, assume that the the reinforced concrete parapet at the roof is 200 millimeters wide by 1200 millimeters high, up to. For the foundation walls, you can use a width between 610 and 630 to match, I guess, the width of your beams. And lastly, pile caps and piles. If you're required to put pile caps and piles under your building, use exactly the dimensions I show on the video for assignment 2. Use that exactly. That's it. I want to thank you for your time, and hopefully this video proves useful to you. Thank you.